But I think as we progress with AI and build up more capabilities, we'll be able to compare these systems with the human mind to see what the differences are. And I think that will also help us to understand better what is unique to humans.
Robots have been portrayed as trustworthy, helpful, and even charming. Despite this, technology has remained elusive for decades, trapped in a domain of science fiction. A breakthrough robotics advancement from Google that moves us one step closer to a future of helpful robots, the Robotics Transformer X, or RTX. So what exactly is RTX? In order to provide robots with a wider range of capabilities for a variety of jobs, Google's DeepMind has partnered with 33 academic labs to release an OpenX embodiment dataset and the RTX model. With more than 500 skills and 150,000 challenges spanning 22 different robot types, this program aims to establish a large digital playground that will advance robotic learning and adaptability. The RTX model raises the bar for robotic performance by combining cutting-edge technologies like transformer structures and cross-model learning. This opens the door for smarter and more effective autonomous systems in industries like healthcare and smart homes. What is Google's new approach with the RTX? Recent research has enhanced robot reasoning, even allowing them to apply chain-of-thought prompting, a method for dissecting multi-step problems. The emergence of vision models such as Palm-E aided robots in better understanding their surroundings. Until now, however, robots were powered by complex layers of systems, with high-level reasoning and low-level manipulation systems operating the robot in an imprecise game of telephone. Consider thinking about what you want to accomplish and then needing to communicate those movements to the rest of your body in order for it to move. RTX eliminates that complexity, allowing a single model to not only do complicated reasoning as shown in foundation models, but also to output robot behaviors. Most crucially, it demonstrates that the system can transfer concepts encoding in its language and vision training data to command robots' actions, even for activities it has never been trained to accomplish, using a tiny quantity of robot training data. For example, if you wanted earlier systems to be able to throw away rubbish, you would have to specifically educate them to be able to recognize trash as well as to pick it up and toss it away. Because RTX can transfer information from a huge corpus of web data, it already knows what trash is and can recognize it without any specific training. It even knows how to throw away rubbish, despite the fact that it has never been instructed to do so. Let us learn in detail about RT2, Robotic Transformer X. In this study, a revolutionary vision language action (VLA) model that learns from both web and robotic data and converts this information into generalized instructions for robotic control, while keeping web-scale capabilities. The approach is based on the Robotic Transformer 1 and 2 model, which was trained on multitask demonstrations and can learn combinations of tasks and objects found in robotic data. More specifically, they used RT1 robot demonstration data acquired for 17 months in an office kitchen environment with 13 robots. RTX outperforms the robotic data it was exposed to in terms of generalization, semantic, and visual understanding. This includes processing new commands and responding to user commands through basic reasoning, such as thinking about item categories or high-level descriptions. Also known that adding chain-of-thought reasoning enables RTX to execute multi-stage semantic reasoning. How are VLMs adapted for robotic control? RTX is based on VLMs, which take one or more photo as input and generate a sequence of tokens that traditionally represent natural language text. These VLMs have been trained effectively on web-scale data to perform tasks such as visual questioning and answering, image captioning, and object detection. In our study, we modify the pathway language and image model, PAL-EX, and the pathway language model embodied Palm-E, to serve as the RTX's backbone. A robot must be trained to do tasks before it can be controlled. We address this issue by expressing actions in the model's output as tokens, analogs to language tokens, and describing actions as strings that can be processed by ordinary natural language tokenizers. The string begins with a flag that specifies whether the current episode should be continued or terminated without executing the remaining orders, and then contains directives to adjust the position and rotation of the end effector, as well as the desired extension of the robot gripper. They also employ the same decreticize from the robot actions as the RT1 and 2, and show that changing it to a string representation allows us to train VLM models on robotic data because the input and output spaces of such models are not altered. What are the generalization and emergent skills from RTX? They conducted a number of qualitative and quantitative studies on RTX models throughout nearly 6,000 robotic trials. In order to investigate RTX's emergent capabilities, they first looked for tasks that would necessitate merging information from web-scale data with the robot's experience, and then they created a 3-skill category: symbol interpretation, reasoning, and human recognition. Each assignment needed a comprehension of visual semantic notions as well as the capacity to operate on these concepts using robotic control. They observed improved generalization performance, more than 3 times improvement across all categories when compared to earlier baselines, such as previous RT1 models and models like Visual Cortex VC1, which were pre-trained on huge visual datasets. They also carried out a series of quantitative evaluations, starting with the original RT1 tasks, for which we have examples in the robot data, and progressing to varying degrees of previous unseen objects, backgrounds, and environments by the robot, which required the robot to learn generalization from VLM pre-training. RTX kept the original tasks shown in robot data and enhanced performance on previously witnessed scenarios by the robot from 32% to 62%, demonstrating the significant value of large-scale pre-training. With this method, RTX can carry out more complex commands that necessitates reasoning about intermediate stages required to carry out users' instructions. RTX can also plan from image and text commands, providing visual grounding planning. Let us look at the advancing robotic controls with the help of RTX. By combining VLM pre-training with robotic data, RTX demonstrates how vision language models, VLMs, can be turned into powerful vision language action, VLA models that can directly operate a robot. RTX produces considerably improved robotic policies and, more crucially, dramatically increased generalization performance and emergent capabilities inherited from web-scale vision language pre-training using 2 instantiations of VLAs based on PaLM-E and PaLE-X. RTX is not only a simple and successful improvement over existing VLM models, but it also shows the promise of developing a general-purpose physical robot capable of reasoning, problem-solving, and information interpretation in order to execute a wide range of real-world activities. What are the learning challenges of real-world robot? The quest for helpful robots has always been a monumental effort, because a robot capable of performing common activities in the world must also be capable of performing complicated, abstract tasks in highly unpredictable situations, particularly ones it has never seen before. Robots, unlike chatbot, require grounding in the actual world and their abilities. Their education isn't limited to learning everything there is to know about an apple, such as how it grows, its physical properties, or that one allegedly landed on Sir Isaac Newton's head. In other words, the RTX robots can learn more like humans do by applying previously learned concepts to new situations. Not only does RTX demonstrate how AI developments are fast cascading into robotics, but it also holds huge promise for larger general-purpose robots. While there's still much work to be done to enable helpful robots in human-centered situations, RTX demonstrates that an exciting future for robotics is just around the corner. Robotic Transformer X is a revolutionary vision language action VLA model that learns from both web and robotics data and integrates this information into generalized robotic control instructions. To acquire a comparable level of skill, robots would need to collect robot data from every object, environment, task, and circumstance. What do you think about Google's RTX? Let us know your views in the comment section. For more interesting updates, subscribe to our channel and don't forget to press the bell icon for notifications. Goodbye.